Today we're going to be talking about velocity and momentum. This can be found in Chapter 2 of our physical science textbook in Section 2. So let's go ahead and get started. So we've been talking about speed, which is an important factor to know. But let's say you get a text alert about a bad hailstorm that's moving at 40 miles per hour, and it is 20 miles north of Rapid City. Should you worry about this hailstorm in your new car or the car that you own in the parking lot of the school? Well, but we really don't have enough information to answer that. What information is missing? So again, we have a hailstorm that's 40 miles per hour moving, and it's 20 miles north of Rapid City. Well, what we're obviously missing is the direction. Which direction is the storm traveling in? If it's coming from south, heading towards the south, which means towards Rapid City, yes, we should worry about it. But if it's heading north, well, that's north of us, so it's already going north or east or west. Don't have to worry about that. So direction is really important. Just know that velocity, the definition of velocity is speed and direction of motion. You have to have speed and you have to have a direction in order to have velocity, okay? And velocity has the same units as speed. It's meters per second because there's no way to add in direction with those units of meters and speed. So we just have to put a modifier. It's going north at 20 meters per second, or it's going south at 20 miles per hour. Things like that, that's how we add our velocity. You know it's velocity when it gives a direction in there, okay? Let's talk about velocity and speed. Find a place to put me, here we go. Velocity and speed, so know that velocity depends on direction and speed. So here are a couple of qualifiers we're going to talk about. So if we have a velocity of an object, can the velocity change if our speed remains the same? And right away, a lot of us think, well, no, if the speed's staying the same, it's not. But remember, velocity is direction and speed. So think about these cars that are going around a NASCAR track. Their speed is pretty much constant, especially if they have those nice high banked corners, but their velocity is constantly changing because they're constantly changing direction. So if your direction change happens with a constant speed, the velocity has changed because we've changed our direction. So can you have a same speed but a different velocity? You can. Think about cars on the highway going in opposite directions at the same speed, okay? So again, remember velocity is direction and speed, okay? Really important, and the reason I'm hammering this home now is because it really matters, and there might be a quiz question or a test question that comes up. Plate tectonics. Why am I talking about plate tectonics? Plate tectonics has to deal with the things on the planet, the plates that float on this surface, that the continents are, as they move around. Well, we talked about them because they move so slow that it's impossible to detect the motion. You would not know that the land mass of North America, the continent that we have, is actually moving. It's drifting on the surface of the planet, but it's going so slow you don't even seem to notice it, okay? So one of the things that we've learned, especially when we have satellites and stuff like that can actually measure this kind of stuff, we know that the continental plates all around the planet move anywhere from 1 centimeter to 17 centimeters per year. That's like hardly moving. How do you know that's moving? All right, well, the theory of plate tectonics states that there are continental plates that move on the crust of the Earth. And as these plates push on each other, the mountains are pushed up and formed, okay? And then earthquakes are also caused by the movements of these plates. Well, this is why we understand why there are certain places in the planet that earthquakes hardly ever happen. Like say here in South Dakota, every now and then we have, like, I don't know, as a kid we had a very, very small one, but there's no active transitional plates anywhere around us. But on California, that's where two plates meet. The continental plate rides on top, and then the ocean, Pacific Ocean plate goes underneath a continental plate. And when those plates rub together, that's when earthquakes happen, okay? So relative motion. Relative motion is all about a choice of a reference point. We talked about those last lecture. And change how motion is observed, okay? Well, what do I mean by this? Well, for instance, let's say this lady standing beside on the road. And as she's standing there, these two cars, the red car and the blue car, are moving past her at 60 miles per hour. Well, to her, both cars are moving 60 miles per hour. But let's look at the driver in the blue car and the dog in the red car. To the dog, the driver in the blue car He's not moving at all because they're both moving at the same rate of speed. Okay? So again, what is the speed of the red car if you're the pedestrian? Well, that's pretty obvious. The pedestrian is not moving, so the speed of the red car is 60 miles per hour. But what's the speed of the red car if you're in the blue car? I already talked about this. If they're both going 60 miles per hour, their relative motion is zero because they're not getting any farther or closer apart. Okay? So relative motion, it's all about our perspective. So let's talk a little bit about this. Let's say I have a rocket that's traveling from the International Space Station and it's going to Mars. Okay? Let's look at some reference points to describe the motion. If you're on the rocket, what motion do you have? Well, obviously, Mars is extremely slowly getting closer to me. It'd be faster because the distance between Mars, it'd be faster to look back behind us and see the space station, and that's moving relatively fast, receding, getting smaller. Okay? If you're on Mars, you're going to see this dot, speck of light possibly, that just stays there for a long time. It doesn't look like it's really getting closer until time passes and the rocket gets very close. If you're on the Earth, you'd see the space station swinging around the planet, and then you'd see a rocket departing from the space station. Okay? Let's talk about it in more down-to-earth terms. We have two trains, and they're approaching each other on parallel tracks, which means they won't hit each other. They're going to pass side by side. What is the relative motion if somebody's standing on the side of the road of the train tracks and watching these two tracks come? Well, if the trains are approaching at the same speed, it looks like both of them are merging at the same time. If, however, one train is going twice as fast because it's a passenger train, and the other train is going half as fast because it's a freight train, it'll look like this train that's passing goes a lot faster. Okay? If you're on the train, it's going to look like the train is coming toward you is approaching. Your speed, relatively speaking, if you just watch the train and kind of forget all the stuff that's flying by out of your side view, is going to look like you're standing still with the train coming forward. Okay? So these are all reference points. It's really important to understand that depending on where your reference points are, the motion will change or appear to change. Okay? We talked about reference points in the first chapter. Momentum. Let's talk about momentum. What is momentum? Momentum is the product of an object's mass and velocity. And there is an equation for that, which is really cool. It's P, a capital P, equals mv. So again, capital P means momentum, m is for mass, and v is for velocity. And we know instinctively that if you have a heavy object moving fast, it's going to hurt a lot more, right, than a light object moving fast. Think about a lineman if you play football. Would you want a lineman to tackle you, or would you want a little safety to tackle you? Well, I'd rather have the safety tackle me because he's a lot lighter. Right? He's not going to hurt as much when he hits me. Okay. So let's look at the formula here and let's figure this out. What would the momentum of a car be with a mass of 1,300 kilograms traveling north at a speed of 28 meters per second? So if we look at our formula, we know we have our knowns is the mass and our other known is the velocity. So mass times velocity, we merely multiply the 1,300 kilograms times the 28 meters per second. And then we end up with 36,400 kilograms per meters per second north. That's quite a lot of momentum. And you can understand now why car crashes, when two cars hit each other head on, it's catastrophic. Lots of bad things happen. Or you guys ever watch a train hit a car that tried to beat the train to the train tracks? It's usually not very good for the car, and the train doesn't even know it smacked the car because there's so much momentum. Okay? Look at a couple other problems here. What would the momentum of a train car be with a mass of 120 tons traveling north at a speed of 50 miles per hour? So again, we're looking for momentum. Our known is the mass and our known is the velocity. Now they're in standard, and since both of them are in standard form, we can use the tons and the miles per hour. We just multiply those across and you have the momentum of that train car, which is quite a lot. Let's look at a smaller instance, okay? Look at something really big moving. Let's look at something really small moving fast. What's the mass of a cheetah that has a momentum of 4,590 kilograms per kilometer per hour and a velocity of 102 kilometers per hour southwest? Well, wait a minute here. So the knowns is actually the momentum and the velocity. So I have to find mass. If we do a little bit of algebra, our formula gets changed into mass equals momentum divided by velocity. So that's actually really easy. We just take our 4,590 kilograms per kilometer per hour and divide that by 102. And then we end up with the mass of the cheetah in kilograms. And that is an actual mass, the average mass of what male cheetahs weigh. All right, and that's it for today. Hopefully you understood a little bit more about velocity and momentum.